It is the shadow that illuminates the world, a dark, viscous liquid that has painted the contours of our modern age. It is the lifeblood of commerce and the engine of industry, a current that connects the entire planet. Each day, more than 100 million barrels are drawn from the earth and sent coursing across continents, a silent testament to the dense black power fueling our world's velocity. This journey begins deep within the planet's crust, where sediments from bygone eras have transformed over millions of years. From these depths, the thick liquid is siphoned upward and channeled into colossal distillation towers. Inside these towers, a meticulous separation unfolds. The raw substance is broken down into gasoline and diesel for our engines, natural gas to heat our homes, and the essential materials that form the very sinews of our infrastructure. After this refinement, every drop is reborn as motion, as light for our sprawling cities, and as the foundational element for countless industries. It's a familiar cry, a simple slogan for a world that can't live without it. For decades, oil has been the very pulse of modern civilization. It is a resource that does far more than propel our cars, ships, and airplanes. It is woven into the fabric of our lives, from the electricity that lights our homes to the plastics and chemicals that define our industries. The slightest fluctuation in its price can trigger a cascade of consequences. Transportation costs climb, the price of goods inflates, and the financial stability of millions of families is thrown into jeopardy. To sustain this colossal need, a heavy price is paid by those on the front lines. On remote offshore rigs and in the dark recesses of the earth, workers endure punishing 12 to 13-hour shifts, surrounded by relentless noise and the constant threat of disaster. The allure of a salary that can climb past $100,000 a year is undeniable. Yet it is a bargain made in exchange for weeks away from family and for a life lived with the ever-present risk of explosions or fatal accidents. It is a profession as unforgiving as it is lucrative, where sweat, strength, and even safety are traded to ensure the current of energy never stops, keeping the modern world in perpetual motion. It is a world without light, crushed by unimaginable pressure. Yet from this abyss, humanity has learned to draw the very energy that illuminates our cities. Deep beneath the Earth's crust, a silent energy lies in wait, trapped for millions of years within ancient sedimentary rock. While this oil and gas has fueled modern civilization, its richest deposits are not found on land, but hidden thousands of meters below the ocean floor. To reach these remote reserves, we have engineered colossal machines, offshore drilling rigs. The creation of these ocean-bound cities begins on solid ground, where giant steel frames weighing tens of thousands of tons are forged in sprawling shipyards. Specialized vessels then haul these immense structures out to sea. At the designated site, fixed platforms are carefully lowered, their steel legs driven deep into the seabed and anchored with concrete, creating a foundation strong enough for waters between 200 and 400 feet deep. But as the ocean floor plunges into trenches thousands of meters deep, engineers turn to semi-submersible rigs. These platforms achieve stability through massive submerged pontoons and thousands of feet of anchor chains, enabling them to operate at depths reaching 12,000 feet, a height 12 times that of the Eiffel Tower. Far below the surface, a critical system known as the subsea wellhead is installed directly onto the seabed. This giant valve, standing just a few feet tall, must withstand pressures hundreds of times greater than those on land, acting as the primary gatekeeper for the flow of oil and gas. Its installation demands surgical precision, carried out to within inches by remotely operated vehicles. In the absolute darkness of the deep, robotic arms maneuver multi-ton steel components, welding them into place and securing the vital pipelines. From the wellhead, a vast network of subsea pipelines begins its journey, stretching for dozens of kilometers across the ocean floor. Each section is welded together and coated with anti-corrosion layers, while continuous monitoring stands guard against the smallest crack, which could trigger an environmental catastrophe. On the surface, towering fortresses known as FPSOs, floating production, storage, and offloading units, ride the waves. Unlike fixed platforms, they are moored by enormous steel chains, allowing them to drift with the ocean's rhythm while remaining tethered to the subsea network. An FPSO can hold up to 2 million barrels of oil, serving as both a processing facility and a massive floating reservoir before offloading its cargo to intercontinental tankers. This intricate chain, from rigs and wellheads to deep-sea pipelines and floating storage, completes an extraordinary journey. It is a system designed to transform energy locked away for eons into the lifeblood of the modern world. Beneath the ocean's immense and silent expanse, a high-stakes search is underway. The journey begins aboard specialized survey vessels, where engineers deploy massive acoustic transmitters into the sea, sending powerful sound waves plunging toward the seabed. These waves reflect off subterranean layers and race back to the surface, where a network of waiting sensors captures their echo. The collected data is then meticulously processed into a three-dimensional seismic map, revealing the ancient sedimentary structures that may have trapped oil and gas for millions of years. But a map is only a promise. To confirm the presence of a reservoir, a drilling rig is positioned over the site. Hundreds of steel pipes, each 9 meters long, are connected one by one, forming a colossal drill string that pierces the water and descends deep into the rock below. At its tip, a drill bit armed with ultra-hard alloy teeth grinds through the earth with relentless rotational force. Once the drill has advanced, the work pauses. An electronic eye, a logging tool packed with multiple sensors, is lowered into the darkness of the well. This device emits electrical pulses, sound waves, and gamma rays that penetrate the surrounding rock walls, sending crucial signals back to the deck. These readings appear as strips of data, revealing the rock's porosity, its permeability, and the pressure within the reservoir. These numbers will determine if a $50 to $100 million well becomes a commercial oil field or a dry hole, abandoned forever. This process is shadowed by ever-present risk. If drilling is mishandled, the immense pressure can surge upwards, triggering a blowout. Crude oil erupting from the seafloor devastates marine ecosystems and unleashes environmental disasters, costing billions to contain. Every step must be executed with absolute precision, for even the smallest mistake can transform an ambitious project into a global catastrophe. It is a force of unimaginable destruction, yet it must be harnessed with absolute control. Once the drill pierces the reservoir, the well bore is fortified, lined with steel casing and sealed with cement to stabilize the surrounding formation. At the wellhead, a colossal steel block known as the blowout preventer is lowered to its post on the seabed. Weighing tens of tons, this guardian houses multiple pressure control valves. They are engineered to clamp around the drill pipe with immense force or shut the well completely in an instant, containing pressures that can surge beyond 10,000 psi and averting a catastrophic blowout. With the well finally secured, the process of extraction can begin. Initially, the raw, natural pressure from deep within the earth is enough to force oil and gas upward through the production tubing. But over time, this reservoir pressure inevitably wanes. To maintain a steady flow, artificial lift systems are brought online, like powerful electric submersible pumps capable of drawing up to 20,000 barrels per day, or gas lift injection techniques. What rises to the surface is not pure oil, but a raw, turbulent mixture of crude, natural gas, water, and fine sand. Directly at the production site, this chaotic flow is channeled into multi-stage separators. Here, the gas is compressed for export or re-injected back into the reservoir to help sustain its pressure. The water, after being treated to remove oil and solids, is discharged back into the sea under strict environmental regulations. The crude oil itself undergoes further processing to strip away salts and other impurities before it is moved into temporary storage tanks. Throughout this entire operation, a network of thousands of sensors acts as a digital nervous system, constantly monitoring pressure, temperature, and flow rates at every stage. Some modern platforms even transmit this real-time data via satellite to onshore control centers, empowering engineers to intervene remotely. If any anomaly is detected, like a sudden pressure drop or abnormal flow, the system can automatically trigger alarms or even shut down the well to prevent disaster. Offshore production is therefore a tightly integrated chain, from managing the flow and separating its phases to treatment, storage, and preparation for transport. It is a stage that demands extreme precision, where the smallest error can cost millions of dollars and leave deep scars on the marine environment. After the crude oil is preliminarily treated and stored, it is ready for the next leg of its journey to shore. For fields located close to land, subsea pipelines stretching for dozens of kilometers carry the oil directly to refineries. In remote, deep-water fields, the crude is instead pumped onto specialized tankers or massive floating storage units, each with the capacity to hold millions of barrels. From there, this ancient energy, formed over eons, begins its voyage toward refineries and ultimately into the fabric of modern life. It begins with a whisper of seismic data, a hint of promise buried in ancient rock. While offshore wells often plunge straight down into the sedimentary layers beneath the seabed, the process on land is far more complex and costly. In the United States, the world's leading producer, this extraction is an intricate and expensive undertaking. The operation starts with meticulous geological surveying and exploration. Engineers deploy seismic waves, conduct exploratory drilling, and analyze rock samples, searching for shale formations with sufficient porosity and permeability to hold oil and gas. Once a promising site is confirmed, the drill bit doesn't just bore straight down. It is steered horizontally deep beneath the surface, carving a tunnel that can stretch for thousands of meters to maximize contact with the reservoir. But to truly unlock the hydrocarbons trapped inside the rock, a method known as hydraulic fracturing is employed. Millions of liters of water, mixed with sand and chemicals, are pumped underground at pressures that can exceed 10,000 psi. This incredible force generates countless microfractures, which sand grains then prop open, creating pathways for the oil and gas to flow out. As these hydrocarbons begin to move, they are channeled to the surface through production tubing. What emerges, however, is not pure oil, but a raw mixture of crude, natural gas, water, and sediments. At the well site, this stream is fed through multi-stage separators, where oil is collected in temporary tanks, gas is compressed for pipelines, and water is chemically treated for reuse or discharge. This intensive process has yielded an enormous output, helping the United States become the world's largest oil producer. Yet the costs are equally staggering. Each well consumes tens of millions of dollars and vast amounts of water, and any mistake in drilling or cementing can lead to chemical leaks, groundwater contamination, or even the sinking of the land itself. Within the labyrinthine heart of the refinery, a transformation of fire and pressure is about to begin. The raw crude oil embarks on its journey toward becoming gasoline, starting with the pivotal process of fractional distillation. This elegant method separates the complex mixture into its various fuel components, all according to their unique boiling points. The process ignites as the crude is subjected to immense heat inside a furnace, reaching temperatures between 650 and 670 degrees Fahrenheit. This scorching environment forces the liquid to vaporize, sending a hot plume of hydrocarbon gas into a towering fractionating column that looms several stories over the facility. Inside, the column is a precisely engineered landscape of dozens of trays, each held at a carefully controlled temperature. As the hot vapor rises, a delicate separation occurs. Lighter hydrocarbons with lower boiling points continue their ascent, while heavier molecules condense into liquid on the lower trays. Near the scorching base, lubricating oils and thick residues settle out, followed by diesel fuel and kerosene on the levels just above. In the middle of the tower, vapors cool enough to condense into gasoline, typically within a boiling range of 90 to 220 degrees Fahrenheit. Reaching the very peak, only the lightest gases like methane, propane, and butane remain. But this newly separated gasoline is not yet ready for an engine. It must endure further refinement, including catalytic cracking to break down heavy molecules and reforming to restructure them for a higher octane rating. Blending then introduces additives that ensure clean combustion, superior anti-knock performance, and lower emissions. Once perfected, the finished gasoline is held in enormous storage tanks, awaiting distribution through a vast network of pipelines, rail cars, and tanker trucks. From a dark, viscous substance drawn from the earth, this series of engineering feats yields a clear, volatile fuel, ready to power billions of vehicles across the globe.